set. And
we are live and go ahead.
Okay, I'll give it one more minute. I think there's still the odd person joining. Okay, so I think I'll make a start now. So welcome back, everyone, for the third day. First up, we have Angelica coming from Cambridge, and she's going to talk about when label data hurts, deep semi-supervised medical image classification with the graph 1 Laplacian. Thank you, Angelica.
Okay, first of all, thank you very much for this kind invitation. It's my pleasure to be here. So for today, I prepared a talk regarding to share with you some works and research line that we have been working lastly a lot. That is about how to learn with minimal labels. And in the end, I'm going to show you that also there are potentials to learn without labels. So today I'm going to focus particularly in a particular task that is the so-called classification. And one of the main messages that I want to transmit in this talk is about can we narrow the gap between model-based approach and deep learning-based approach? And can we get the best of both worlds? So just let me start. So first of all, I'm going to start with a motivation from a general point of view, why in this era of big data is very convenient to use or design algorithmic approach that requires less labels or minimal labels. And this is from a general point of view, and then I'm going to narrow more to a particular question. Can we design an algorithmic approach that can recreate the performance of supervised learning, but taking a model-based approach and take the best of deep nets, and that's the so-called hybrid models. I'm going to talk about these hybrid models, how to propose a new model-based approach, and how that can be connected to deep nets. And then I'm going to focus in a particular case study that is the medical domain. So, but I'm going to show you also that there are this algorithmic approach can be used in a different kind of context or domains, like for instance, natural images and so on. And finally, I'm going to close my presentation with the concluding remarks. So starting with the motivation, I would like to start my motivation by using a phrase that we hear everywhere else, that is pics and videos or it didn't happen. And this is really true, because if we stop for 1 second to think about how many data we are producing every single day, it's really mind-blowing. It seems like we are living in online, our lives are online. So just to give you a big picture about what I'm talking about, let me show you some numbers. So common example, for instance, is social media. So if we take a look about, like, for instance, some examples, like, for instance, Instagram, Facebook, we are producing per hour or every single day in the order of millions of pictures every hour, like, for instance, in Facebook, or 95 millions every day. And from that, we can have other complex data, like, for instance, video. Some example is, like, for instance, YouTube, that we are producing more than 300 hours every minute. And these numbers has been increasing substantially during the last months. But this kind of phenomenon about the vast amount of data that we are producing is not just relying or is just about social networks. It's happening in any domain. Like, for instance, the remote sensing domains, where you want to capture online or analyze some measurements at distance, or as well the medical domain. And this particular domain is the one that I'm going to focus and give a case study for our algorithmic approach. So, but the main question here is about how we can gain insights into this data. So because we can produce vast amount of data, we can have huge amount of data, but all this data doesn't have value until we find a particular application. So saying that this is one of the biggest questions in nowadays, how we can gain insights. So someone can just raise up the hand and say, well, I just hear that we can use machine learning. Now can we go home? But this is not straightforward. Through this talk, I'm going to show you that there are a lot of challenges, particularly in some particular domains, like for instance, the medical domain, where a label is really really needs expert knowledge or involves financial cost and time. Okay, so particularly I'm going to focus in a task that is called classification. So how we can define classification? The best way to do it is in an illustration. So let's say we have different objects or animals, for instance, here, let's pick one, for instance, a cat. So the cat can be represented by different descriptors. That means that we can have cats that they have different sizes, different colors, and so on. So the classification task means that having a set of predefined categories, given a new sample, assigning one of these labels. So this is the task that I'm going to be discussing today. So, but if we take a look about the body literature in classification, we are able to see that one of the major assumptions here is that all algorithmic approach rely on having good and large and well-representative corpus of label data. And actually, this is a strong assumption because in different domains, like for instance, the medical domain, a single label needs the agreement of a set of experts. So, and that's why I want to motivate the semi-supervised approach. And I have seen that in previous days, many people have talked about the setting, and I'm going to as well connect the model-based approach in the setting, but as well recent developments in deep learning. So why semi-supervised learning is a perfect fit now in this era of big data? Well, first of all, because label data is very hard to obtain. And particularly, for instance, in domains like the medical domain, is very expensive and time consuming. And as I mentioned before, a single label requires expert knowledge and increased financial cost and as well time, or simply because your graduate student is on holidays. So, but as I mentioned before, this is not just about social networks. Any domain, we aim or we seek to depend less on this label data because each label data, they have some level of uncertainty. So that affects our algorithmic approach or the performance. So these are some just examples about where a semi-supervised learning can be perfectly, just ranging from social networks, functional networks, 3D shapes, etc. So, but the particular domain and the case study that I'm going to talk about today is about the medical domain. So, sorry, yes. So, but what is happening in semi-supervised learning? Why is it interesting to explore this paradigm? Well, semi-supervised learning has been out there for many, many years. There has been developments, there are a lot of developments and promising techniques since early developments in the area. But if we take a look about in the past, this is the thoughts that we have. So we believe that the research community, everyone believes that the label, while you have more label data, that means that you're going to have more performance. So the go-to technique or paradigm used to be like supervised learning. And this used to be like the performance regarding semi-supervised, the one that is in the red line. But what is happening in the last perhaps 3-4 years is something in the community that is called the quiet semi-supervised revolution. So what is happening? All the underpinning theory that has been existing for years in semi-supervised learning can be used or do an analogy to recent developments in deep nets. And what is happening now is this so-called magic zone. So the performance of semi-supervised learning have shown to be recreating and sometimes outperforming the performance of supervised techniques. And this is why we are very encouraging to explore new areas of semi-supervised techniques. But this magic area mainly has been reported on pure deep learning approaches. But what is happening in pure deep learning approaches? We are not able to say anything particularly about some mathematical guarantees and so on. So one of the main goals here in my talk is, can we use these recent developments, but also as well a model-based approach to recreate or outperform semi-supervised techniques for classification. So, and this is another motivation for doing that, because there are different domains where label data is scarce. And the domain that I'm going to be exploring is a medical domain. So why the medical domain is a perfect fit? Well, a single, let me give you some examples that we are able to see here in the slide. For instance, in the terms of mammograms, if it's, for instance, different type of cancers or so, many times, or majority of times, they need at least 2 readers to agree on the label. So this kind of agreement of the label is expensive, increased financial costs and time, of course, of the evaluation. So this is that happened not just about, for instance, this particular case for mammograms, but in other cases, like for instance, when you want to take a look about any pathology in chest X-ray, that is another example that you're able to illustrate here, or as well cells. So, and we have to take into account that even if we have the labels, there is some human bias. That means that sometimes the agreements are not able to reach, the experts are not able to reach an agreement, so there should be some uncertainty. So they need to call for a third or more experts to just label a single sample. So while we have more uncertainty, of course, the algorithmic approach are more effective in performance-wise. And this is why there is the motivation why we are exploring, lastly, semi-supervised in a hybrid context. So what I mean when I say hybrid models? Well, if we take a look about the taxonomy in semi-supervised learning, they had changed a lot in last years. So let me give you the big picture. I'm not going to go into details here, but just to let you know what is the context of this talk. So before and recent and early development has been focused mainly on model-based techniques. So these are some examples. Of course, there are a lot of like seminal papers, but I just put few of them to illustrate this context. And in recent years, there is this wide revolution that is pure deep semi-supervised techniques. And there is the so-called hybrid models. What is hybrid models? Means that can we narrow the gap between model-based techniques and deep learning techniques. And this is one of the motivation of this talk. Can we have the best of both worlds? And as I mentioned before, this is a big picture in the taxonomy, because we have a lot of sub areas like graph-based techniques, generative model, proxy-based techniques, or one of the major ones that is currently going on, that is consistency regularization, or the so-called perturbation-based techniques. And I'm going to discuss that and the connections between this model-based approach and deep learning approach. So before to go to explain the or algorithmic approach, I just want to step for one slide to mention what are going to be the contributions in this talk. Well, first of all, we aim to recreate or outperform the performance given by subclassification techniques in the supervised context through hybrid techniques. So our hybrid techniques, and what I'm going to talk today is about multi-class classification functional that is based on the normalized and non-smooth Dirichlet energy associated with the P Laplacian. And once I finish talking about this multi-class functional, I'm going to talk about how this one can help, or how deep nets can help to improve or boost the performance of this multi-class functional. And then I'm going to show some case studies with different data sets ranging from the medical domain, for instance, chest X-rays and so on. But also I'm going to show you that this technique can be applied to other type of images, like for instance, the natural images. So let's start talking about the model. So before talking about the model, let me give you a couple of preliminaries here, what is going to be about the work. So we are talking about the semi-supervised setting. So the main objective here is that we have a huge amount of data where out of this huge amount of data, we have just a tiny label sets. So the main goal is using this tiny label set, can we infer the labels that are predefined categories from the huge amount of label sets, and hopefully with minimum generalization error. So this is the context that we are going to work in today to design our approach. Of course, as I mentioned before, semi-supervised learning can take different perspectives. One of that perspective, as I mentioned, is graph-based techniques. And this is the one that is going to be the focus of my talk. So in graph-based techniques, the main goal can be illustrated in this figure. So we have a graph, where each node in this top is going to represent a single image. So, and we have a set of labels. So each color here in this label represents a class. And the assumption is that we have to know the classes. We have to have at least some samples of label samples of per class. This is the assumption. That means that we are not able to discover new classes. Like for instance, if there is another new pathology that I haven't seen before and so on. So the main goal is having these label sets. Can we propagate this information to the rest of huge amount of unlabeled data that are these great nodes that you're able to see here. So in the end, we are going to have some outputs that looks like that, where, as I mentioned, each color represents a different class. So for that, I'm going to first talking about this model-based approach in recent work that we have been working on. And then I'm going to talk about how this model-based approach can connect with deep learning, and in particular in a sub-area that is called proxy-based techniques. So let me give you very quickly some preliminaries about the context that we are going to be working on here. So we are going to be working on convex and absolutely p-homogeneous non-local functionals that they have this form, where U are going to be functions defining of a set of nodes. W, we have the weights, and D are the nodes degree. So if we take a look about this scheme, it looks quite familiar because many researchers have investigated that for different cases. For instance, in the case where P is equal to 2, we have, for instance, the SUA paper to the so-called seminal paper from local to global consistency, and so on. From there, different algorithmic techniques has been developed, for instance, approximating P to 1, and so on. So our motivation that is to take a look about this scheme, but in a particular case. In the case where we have P equal to 1. Why is our motivation to do that? Because recent developments in machine learning have shown that actually for this particular case, offer better clustering performance. So saying that, we can rewrite this form using the P equal to 1, defined on a functional J, a function J that is going to be one homogeneous function. So where we have an n times n diagonal matrix D containing the degree of nodes here, D. So, and this is going to be the context that we are going to use for design our algorithmic approach. So I'm not going to touch upon about some set of possible subdifferentials in here for J, but I'm going to give you the reference to go in details later. But what I want to talk and mention very quickly is about eigenfunctions. Because this is really like a fundamental tool to provide a relevant clustering of the graph. So when we talk about eigenfunctions, we can take a look about the literature, and different methods have been developing to estimate such eigenfunctions. Through, for instance, the local minimization of the gradient quotients. Here are some examples of such works, and where we have as well another one homogeneous function H here. So of course we can take L2 norm here, and we can recover some eigenfunctions for J, or we can take L1 norm here, so we can compute, as having shown in other works, the value functions that that are local minima of this region. So and as well, when we take a look about this scheme, might be look familiar for us, and indeed because they have a close relation with other schemes, like for instance, Chigger cuts, balance cuts, and so on. So, and this is exactly the context that we are going to use for designing our algorithmic approach. So let me, saying that our preliminaries, let me go to talk about our algorithmic approach. So first of all, as I mentioned before, I'm going to have two parts. One part is the model-based approach, where the model-based approach involves to talk about a new functional, multi-class functional. And the second part is going to be how we can connect this model-based approach with deep nets, such that we can take advantage of the powerful performance of these new developments in machine learning. So I'm going to try to do a trade-off between the time to explain and give the big picture of our approach. So our approach starts with just want to clarify that we are in the multi-class setting. So we can use that algorithmic approach as well in the binary case, but many real-world problems we have to deal with the multi-class case. So we have a multi-class setting. And now what we aim to do is to find L-coupled functions of UL that are actually local minima of a ratio of these two one-homogeneous functions. So, and this issue is nothing but the problem of having or defining a good coupling constraint between U or ULs, such that we can project easily on. So for this particular work, what we use is a simple linear coupling constraint that iterates in this way. So, but someone can think about other coupling constraints that are out there or are very like well-defined, like for instance, the classical simplex or the orthogonality constraint. This is just some examples. And what is the main motivation to use this simple linear coupling constraint? Well, because if we take a comparison against the classic simplex, we can notice that actually this simple linear constraint is less expensive, offering less expensive projections that this classic simplex. So this is one first motivation. But what happened in comparison with the orthogonality constraint? Well, in that case, we have to deal with non-convex problems in our ULs. So that's the first point why we can use a simple linear coupling constraint. So we can save this for the next part to where we define our functional. So just as a reminder, what we are considering here is the minimization, this minimization problem, where we have two one-homogeneous functionals, J and H. So the main problem here is how we can find a good local minima of this problem. So there are different ways. The one that we are going to present today and discuss recently is a functional, an iterative multi-class functional that operates in this way. So we have a time step delta that is greater than 0. We have R that is referring to the ratios over functions that I mentioned before, J and H. We have this SUFI differential that I didn't went in details, but I know to show you the reference such that you can see every single step on that. And we have J that is our another one homogeneous function, and this term is related to the constraint, the simple linear constraint that I discussed before. So, and this is the one that we are going to considering. So the question is how we can solve this problem and how we can solve this problem, and then how we can connect it with deep learning to generate a hybrid approach. So just a reminder, as a reminder is that we are in the setting where we assume that we have some labels in the nodes. So we have knowledge about each category that we have at least few samples. So this is just a reminder to take a look about it. So now the question is how we can take into account or how we consider a solution for this multi-class function. So to do that, let me check. Yes, here. So what we can do is an iterative scheme. So in here we can have a starting point in U0 that satisfies our constraint, the simple linear constraint that I talked before. So and then we can do our interactive method or iterative solution as you are able to see here. So of course we can see and talk about some convergence of these guys. But I'm not going to go in details in the convergence because I want to talk about the connections, how we can connect these with deep nets. But the key of this is that actually this guy that we are able to see here is a global minimizer actually of FTK. So based on that, we can actually show some convergence in the trajectories. So this is the scheme and the functional that we are going to consider in this work. So for the final labels, what we have is that once this is converged. As I mentioned before, I'm not going to go into details in the convergence. I give you some key about how we can show this convergence of this functional. But once it's converged, what we can take is the argument of maximum of this interactive scheme. So, but the main question here is how we can connect this scheme with deep nets. Because so far we're talking about to use, for instance, to solve this, I forgot to mention, like the primordial algorithmic approach algorithm. So how we can do to connect, how we can connect this interactive scheme to deep nets. And this is what I'm going to talk about in the next couple of slides. So the main question here is how can we connect this model-based approach that I mentioned before and with some deep nets? The main goal is that deep nets can give you some generalization of the feature space, so you can construct a stronger graph. And therefore, you can have like a boost the performance of the classification task. But how this can be achieved? This is the, one of the questions. So for that, I will give you like a quick look about the recent trends on deep semi-supervised learning, how hybrid techniques can be to a different line of research that this trend, and how we can, in the end, connect this model-based approach with a deep net. So the main question is, the first question is what we can gain for deep nets. And what is good about deep nets is that we can actually have a better, for instance, in this case, in the graph sense, we can have a very strong feature or generalization of the feature space to construct a stronger graph. But how they can be achieved? Well, if we can ask you, like, if this is dog or a fried chicken, sometimes we need some time to differentiate. And we have been trained to differentiate these images and these classes, still is complicated sometimes for us to take some time to differentiate these particular classes between fry and chicken. Or also that can happen for several cases, like for instance, you have a Chihuahua or muffin. So, and this is exactly where we can help model-based approach. Can we get these descriptors that can differentiate, or these embeddings that can differentiate these classes in a better way? Because even for humans, is sometimes complicated. We need, not complicated, but we need some time to differentiate between these two categories. So this is where deep nets are good at. And this is the motivation why we can connect the model-based approach with a deep net. So what I'm talking about. So before to go in details, before to talk about how this connection can be done, let me give you a very quick look about the current trend on deep semi-supervised learning. The current trend is the so-called perturbation-based methods. And this is in the context of deep semi-supervised learning. So what is the main idea here in perturbation-based methods? So it has to deal with, the label sets. So inducing any perturbation, delta perturbation, what we aim to do is that actually the output, or guarantee somehow that the output is not going to be changing under any delta perturbation. So let me give you a quick look about what I'm talking about. This is a very, very big overview about this area of deep semi-supervised learning. So we have, when we talk about perturbation-based methods, we have a loss that is concerned to the supervised context. And this supervised context involves just the tiny, very, very tiny label sets. And we have another term that is related to the label data. So, and this is where perturbations plays a good role. This is the perturbation-based method, or so-called consistency regularization. And this has been shown, explored in many, many works. And the main idea is that, can we have a label sample? Can we perturb it, have some delta perturbation? And can we have, can we enforce that these perturbations, either it is a strong perturbation, a weak perturbation, can be robust to this initial unlabeled sample? So, and this is the other term for the perturbation-based method. So in the end, we have some sort of loss that involves supervised loss, and we have to involve the label data with some gamma parameter, positive gamma parameter. So, and this is some of the trends on current deep semi-supervised methods. One of the major problems is how we can define these delta perturbations. Are they feasible? Can we say something about, because some of these perturbations might be close to the low boundary separation, but some of them no. And actually, one needs to be careful about how to define it, because if you define it in a no good way, instead of improve or achieve this consistency, what you're going to do is affect the performance. But as I mentioned before, this area is developing very, very fast. There are some new developments where there are actually a good way to define these delta perturbations, like for instance, some techniques like a run augment and so on, where you can look in the space of all these perturbations, one might be the more feasible for your approach. So this is an example about what I'm talking about when I say perturbation. So we have X that it belongs to the label set. And here, I don't know if it's visible, but we have some delta perturbation in this output. And then we can have a different perturbation, another type of perturbation in the same input image. So maybe it's visible in this area when this delta perhaps is more visible than in here. So these two are different perturbations for the same X that is in the label set. So but this is all about deep learning context. The main question is how we can go beyond this current trend of perturbation-based methods and connect the model-based approach and deep nets. So what I'm talking about is in the next slide is how this connection can be possible. We aim to avoid somehow to define explicitly these delta perturbations. And another way to go around that is use another philosophy, like for instance, proxy-based techniques, like in the context of, for instance, pseudo-labeling and so on. So saying that, the main objective is, or the next slide is how we can do this gap between these techniques and model-based techniques. So let me give you overall like context about how it's done. So we have as our label or tiny label sets, and we have the huge amount of unlabeled data. So what we're going to do is use a deep net to have generalize the feature extraction and space, so we can have better evidence for construct the graph. But before to go in details about how it's done this, let me remind you more formally in that if we think about just deep semi-supervised learning, that is the general picture that of the laws that we have to deal with. That means that we have a term that involves the supervised context. This one, supervised, means that we have to take into account just the tiny set of the tiny label sets. So this is what I meant when I say supervised. Because in the supervised, semi-supervised context, you assume that you have some labels. And the second term is about dealing with the unlabeled sets. And this parameter, gamma parameter, is to find a trade-off. So this is the big picture about deep semi-supervised learning. So, but how we can go from this to the model or the multi-class model-based approach that I mentioned before. So this is the question that I'm going to answer next. So let's assume first that we have a net, a deep net, that is this F theta, but this net can be decomposed actually. We have the feature space actually and a full connected layer part in the end. So we can take this feature extraction part to get some better impedance to construct the graph. So what is the key ideas that we are going to use? So as I mentioned before, one of the things is that can we go around to define exactly these delta perturbations and go in a different way to solve the problem? So something that is or looks interesting for us is the philosophy that is called pseudo-labeling. That's the first paper was by Lee in 2013. But in this context or in this algorithmic approach from Lee, the main idea is to generate these pseudo labels from the network inside. So you don't have this part itself. So and this is where I'm going to explain how the model-based approach plays an important role here for the performance. So pseudo labels means I'm not going to go into details because there are a lot of concepts that are involved here. But just to give you the big picture is that pseudo labels means that you have the net and you have the huge amount of label data. You have the tiny label set. You train the network to have some inference of this label set based on the tiny set. So this is going to be your pseudo label. So you can later refine these uncertainties that you assign to the initial label set. So this concept, it was interesting for us, and we see it as a somehow mitigate how to define these delta perturbations. And there are some other recent techniques as well that go around as well to generate these pseudo labels. Instead of generate it to the network itself, you can generate it actually outside the context, using, for instance, in this work, using some like a graph Laplacian, but in the case where P is equal to 2. So saying these key ideas, let's go to take a look about how we can connect finally our model-based approach and the deep net. So we have first to have somehow to say we need some initial guess to construct the graph. So what we need to do for initialization is to use the huge amount of label data to have the tiny label set filled in a network. From that, we are going to have some good generalization of the features and impedance that we can use to construct the graph as the initial point. So once this initialization is done, we just do it once for initialization. Then we forget about this. The next is how we can involve this model-based approach and in an iterative way to refine these pseudo labels. So the main driving optimization here is the iterative scheme or the functional that I talked before. That is this main scheme that I discussed in the previous slides. So we have initialization. One time we can construct the graph. Now we have the graph. We can do this propagation or this propagation on the label data using the multi-class functional that I presented before. But these are considering pseudo labels. So that means that still there are a lot of uncertainty on the initial guess. So what is the best way to iteratively improve these uncertainties or guesses in the pseudo labels? So we can take, this is a big picture about the deep learning setting. In particular, what we use actually in semi-supervised, in the supervised loss, the most common choice is where there are different choices, but the most well-known is, for instance, cross-entropy loss. So we use that for the supervised part. And for the unsupervised, for the on-label set, instead of using the current trend that I mentioned before about consistency regularization, what this one is going to involve is actually these pseudo labels that are going to be generated by the multi-class functional that I mentioned before. So just to summarize, it's going like that. Initialization, we have an initial graph. We can construct after this extraction of the features first, the initial graph. Then we can do iteratively this main driving optimization, propagate the labels. Then go inside somehow to mitigate this uncertainty because the initial guess for these pseudo labels are going to have high uncertainty. So we can again deal with this net and say how good is this inference and so on. So we can go iteratively over these two optimization parts. So okay, I need to go, I think, now to the experiment results because of the time, but this is a big picture. There are many concepts here, like for instance, what happened where you have imbalance case, that it happens a lot in the medical domain. Then with imbalance case, I mean, like, for instance, you have different pathologies and you have more samples of a particular pathology than the other. So there is some concept behind cost-sensitive learning, for instance, to deal with that, or simply some parts that you can mitigate based on the ratio of your of the particular classes that you have. So there are some concepts that I'm not going to go in detail today because of the time, because I want to share with you some experimental results. But just to give you a big picture, this on-label set involves these pseudo labels generated by the model-based approach. And this is how the hybrid models can be connected, this model-based approach and the deep learning-based approach. But the question is it really, how is the performance in real-world scenarios? And when I talk about real-world scenarios, I meant like tackling like a huge amount of label data where any node, a single node in the graph means has image, for instance. And this image can be, for instance, in the context of medical domain. And I'm going to give you a case study now for the experimental results. Yes, so some experimental results, let me show you. So the first case that I want to share with you is about the medical domain. So we have chest X-rays. So this data set was released in 2017. It's one of the benchmarking for chest X-ray, where you have mainly 14 classes. So each class means a pathology. So just examples of these pathologies are illustrated here. Like for instance, you have consolidation, pneumonia, and so on. So you have 14 classes now. You have more than 100,000 chest X-rays, and this is the data set that we are going to use to compare. So majority of the benchmarking are, or the algorithmic approach that are out there, involves supervised techniques. So our first question is going to be, using our hybrid model, can we recreate or outperform the performance of the existing techniques for chest for this particular benchmarking? So let me show you some results in this context. So we have here the data set chest X-ray. So these algorithmic approach are related to the unsupervised case. The fully supervised techniques where they need 70% of the label data. While our approach that I mentioned, that I talked about that before, the hybrid model, we use 20% of label data. So of course, one question is going to be, why not increase these percentage of labels? Why not increase it? So, well, we have to define the boundary when how much label might be considered semi-supervised. And there are different works on that, even in recent developments, like Joaquin's papers, where they show that actually when you increase more and more the label sets, you are actually losing the bonus that is given this constructive setting. So we have 20%. If we take a look about the comparisons I mentioned before, these ones are supervised techniques. This is a metric area under the curve that we have over all the classes that I showed you before. So we are able to say that in many cases, under similar, offering more or less labels data, we are able to recreate several of these performance for the supervised techniques. Of course, there are other supervised techniques that are outperforming of technique, but we are in the way to, or there are different ways to improve our current algorithmic approach. So this is a big picture about these chest X-rays. Something that it was interesting for us to take a look about it is about these results, is related to the official partition. But what happens when you have a different random partition of the data? That means that you have, you are not using the official one that is separated to use explicitly what is the training and the test, but you have the whole data and you do some random partition for the label set. So we are able to see that actually, while you do this partition and you change it different from the official partition, actually some approach, like for instance, one approach decreases. And the main reason for that is because supervised techniques rely on these very representative data sets. So there are different pathologies that they have really highly imbalanced cases. So with these highly imbalanced cases, you are able to somehow to affect the performance. And this is where we observe it here in WAF technique. Yes, so this is a quick look about per class comparison for all the techniques. These ones are supervised techniques versus our techniques. Of course, there are some classes that, for instance, other approach like a junk that overall outperform the best performs really better per class in comparison that ours, that is the pink one, this bar that is pink one. So this is just a quick look. Let me go very quickly to the next experiments. I noticed that I'm running out of time, so sorry for that. Let me go very quickly to the experiment. So, but of course, this type of algorithmic approach, we can use it for different contexts, different type of data, like for instance, natural data, natural images. So this one is a very well-known data set that is called C410. And we have 10 classes, and this is the size of the images, and this is the number of the images. So, but the question is, let's go to investigate the current deep semi-supervised techniques. And the question is, can we recreate or or competes, readily compete with pure deep semi-supervised techniques. And this is a comparison. All of these techniques are deep semi-supervised techniques. Of course, there are different techniques that are missing here from recent years. We have the results, but I'm not going to display it today. But just to give you a big picture about that, we can see that actually we can recreate most of the time this performance, and in sometimes outperforms for some label counts. But it's worth to mention here that, for instance, the type of network that we use is very shallow. It's not like a big nets, because as there are different open questions that I will discuss in the future work. Sorry, so I should go ahead and present. So we have other data sets, like for instance, CFAR 100, where you have 100 classes, and this is like a very quick look on the results. So what happens when you have 100 classes, and are we able to combine our algorithmic approach and scale it to other, combine it with other philosophy in deep semi-supervised learning to boost the performance? So this is some quick results that we have on CFAR 100. We are able to see that compared, for instance, with this technique that use the case for p equal to 2 with deep learning, we are able to outperform this technique. And we have other results for mini-marginate, CFAR, and other techniques like recent developments like a mixed match, and so on, but I'm not going to present it today because of the time. Let's go to the concluding remarks. So what is the message to take home here? Is first of all, hybrid models have shown a lot of promising results here in this area. And we can show that actually deep semi-supervised learning at this point in time is in a good position to readily compete with pure supervised techniques. So this is really like encouraging for research, and particularly in contexts like the medical domain, where, as I mentioned before, a single label is really highly expensive or involves a lot of human bias. So we show that actually there is a promising results that our technique is able to compete with supervised techniques, but at some of them I mentioned that are better, but the main goal or the strength of the technique is that we are using just 20%, very a tiny set of label sets. So of course there are different ways to improve the techniques. There are different open questions. This is not the ultimate approach. We are investigating how to push forward these results and in a different, addressing different questions that I'm going to show like in our next slide, future work that we have in mind and questions. So, and finally, another message to take home hybrid models is that we can somehow say something about the model in a model-based approach, but at the same time, take advantage of the performance of deep nets. So, future perspectives, there are a lot of open questions. What about minimal labels? What about no labels? And this talk is mainly focused on this paper that we have here, but also we have other cases with p equal to 2. You can take a look about this other paper. And I'm going to give you very quickly in one slide what are the open questions that we are taking a look about it, and works that are really in final stages. So what is next? There's a lot of open questions here, like perturbation-based methods. Can we define some feasible perturbations? Can we do this analogy of pure deep learning approach to graph-based techniques? Can we keep these hybrid models and say something about these perturbations improve the performance? There is something that we are taking a look about it. So how to define these feasible perturbations? Some of them in the literature, there are a lot of concepts like a strong, weak perturbation and so on. So also as well, we are able to investigate, can we learn with minimal labels in a particularly with data sets that you have minimal information? There is something that we are as well in final stages. And of course, this one can be, as I mentioned, it's not just about medical domain. You can apply it to different contexts. Like for instance, outdoor images like this, where you don't have images, but how to deal with the dynamic, because you have to involve video. So can you use deep semi-supervised techniques with video data to do, for instance, in this case, semantic segmentations? So this is another work that we are now. And another thing that for us is like very encouraging is what about to use no labels at all? Can we use and reproduce good results with no labels? And this is something that we are able to, we are currently doing, like explore beyond semi-supervised learning some paradigms related to unsupervised techniques. So with that, sorry, I'm running out of the time. My apologies. That's all. Thank you very much.
Oh, thank you very much, Angelica. That's a great talk. If there are any questions, I please encourage people to either raise your hand or put them in the chat. I'm happy to start things off though, whilst people are sort of typing away or thinking about what they want to ask. So one thing, maybe I missed this or I didn't quite understand this, but in the unsupervised part of the loss, are you using the geometry from the graph?
So when you say the geometry of the graph, can you explain exactly what you mean with this?
So I'm being quite vague. I mean, I guess in some ways, okay, so yes, I think this is probably the perfect picture. So in okay, so you're kind of iteratively trying to learn the graph. This is what I kind of understand. And in some sense, you can see the graph as being, it's a manifold, and this kind of, parameterizes your data space. Yeah. And so this kind of tells you then what the geometry kind of looks like. So now if you're looking at, so in the unsupervised parts of your loss, you're looking at perturbations. Now, of course, it seems reasonable that you don't want to take a perturbation that takes you away from the sort of the image manifold. You want to sort of stay on this manifold. And so, I mean, are you trying to use that information?
Yes, actually, this is a very good question, actually, because I want to mention that this is one of the difference, because in perturbation-based techniques, as you mentioned, the main consistency is based on these perturbation data. So you have these unsupervised techniques, you have a sample input in the label set, and you perturb it many times as you want. So this is the consistency. You need to find a feasible what is called feasible perturbation augmentations. But in here, what we want to do is try to mitigate that part, actually. So we instead of having these perturbations in the unsupervised part, what we have here, and I didn't go into detail, sorry for that, is we have actually over the pseudo labels. That means the pseudo labels produced in here. The perturbations are going to be at the beginning of the process, but these perturbations in this loss are not going to be involved, but it's more in terms of pseudo labels parts. So that means that these pseudo labels means that you have this model-based approach giving you an initial prediction of the label data. You put it here, and you can see it like you can use another cross entropy, for instance, when you have this label for this sample on label data that it has some pseudo labels, and for the next iteration you have another one. So you have to sort of mitigate this this gap between this certainty between these pseudo labels.
Okay, I guess a related question is that I think it's now kind of quite well documented, sort of the neural networks are very unstable to perturbations. I mean, are these sort of, are they better, or I mean, what have people observed? Yeah,
for perturbations, yes. This is actually another good question, because if you take a look at, maybe I can I can answer giving you an example. Like for instance, let me give you the example or list of here. Like, let's take a look about, for instance, Miyato. Miyato, they have like a sort of virtual adversarial training for perturbations. So what happened here? Here are very sensitive. Depends of, you have to be very careful how to define these adversarial examples here. But, and this is what has been one of the major problems here. And if I understood what your question is, how to mitigate these perturbations. There are recent works, like for instance, Chie, the UDA, and so on, where these perturbations go around and they use some other techniques, like for instance, the so-called run-of-main. So run-of-main, what it's saying is, can we find amongst all these perturbation space, some feasible perturbations that actually are not affecting the performance? And this is, has been done in recent works about how to go around to define explicitly this delta. So earlier works like this, you can find some perturbations even starting from similar, like besides noise, some other kind of perturbations, like a weak perturbation. You just have your image, perhaps you translate it and rotate it, and this is a weak perturbation. But what happens if you have strong perturbations? That means that, for instance, you have different levels of color, you have to deal with intensity changes and so on. So you have more strong impact in the perturbation. So but there has been a problem for previous techniques, but recent techniques is not completely solved, but they have find ways like some techniques, like for instance, this that I mentioned, random range, to find some feasible parts for these perturbations.
Okay, thank you. Okay, if there are no questions, I suggest we go to the break room so people can ask more questions there. I think once you're in the break room, you'll be able to unmute yourself. Yeah, so yeah, thank you again, Angelica.
Thank you very much.